Yeah, introducing Nathaniel. Um, I'm gonna let you introduce yourself and get started. I think by default we'll be having there'll be questions during the talk if people are confused about stuff. And then I'm gonna try to prevent there being too much back and forth, and we'll save bigger questions until the end. But given that it's like a small audience today, we probably have quite a bit of time to understand the technical details of what's going on, which should be exciting. So yeah, without further ado, Nathaniel.
All right. My name is Nathaniel Virgo. I'm an associate professor at the Earth Life Science Institute, which is in Tokyo. I'm going to present a small part of a bigger collaboration with my colleagues Martin Beale, Matteo Capucci, and Manuel Baltieri, and it's quite closely related to work that I'm working on with, or have worked on with Simon McGregor and Tom Meck, who likes to be called Tim Moore. So, and the research is funded by the John Templeton Foundation. So my general goal in this research is that I want to understand agents mathematically. Like, what is an agent? And when I say agent, so I think people in this field often mean, when they say agent, they often kind of mean optimizers or like something very sophisticated. I don't necessarily mean that, although I don't exclude it. The main thing I'm interested in is, what does it mean for something to act or have knowledge or beliefs or have a goal? And so human beings can have those things. Humans can be agents, but also biological cells are agents, so as trying to do something, to eat or reproduce or whatever. Perhaps a little harder to say they have beliefs, but they certainly have senses. They engage with the world in an agency sort of way. And the thing on the right is supposed to be a Roomba, and that's just to say I don't exclude robots or simple things from being agents. I don't think there's like some magic thing that living things have that robots don't have. And like even understanding what it means to say a Roomba is an agent would be interesting, would be progress, right? Because a Roomba, you'll look at it sometimes and you say, oh, it's trying to get around the corner or whatever. It kind of seems like an agent. I take the as if approach to agency, or this is what my colleague Simon McGregor and your colleague Simon McGregor calls the as if approach. But it really goes back to the famous philosopher Daniel Dennett. The idea is that the question to be asking here is not, is this thing an agent or not? But simply, what does it mean to treat something as if it were an agent, right? Because the Roomba doesn't have any magic source in it; it's just a thing. But sometimes we want to treat it as if it's an agent. And then Dennett's idea is that that a human being is kind of the same. So a human being is just a big collection of actions moving according to the laws of physics. And if you wanted to and had the resources, you could try to predict their behavior using the laws of physics. But this would be extremely difficult. Whereas if you look at a human being and try to kind of figure out what they're trying to do, that's often a very good way to predict their behavior. So the idea is that you always have the choice for any system whether to regard it as an agent or just as a physical object. But for some systems, regarding them as an agent, taking the intentional stance is much more informative than for other systems. And so ultimately, I want to understand why that is. I want to understand what makes the intentional stance more informative for some systems than others. Today, I'm not going to get anywhere near that, but I will get a little bit towards understanding like what the intentional stance actually is mathematically. At least that's the block I'm hoping to chip a bit off today. So I want to mention some related work that I've done before on understanding what it means for one system to model another system or to have beliefs about another system. So this is kind of an important part of the rest of the talk. So the idea is that to treat something as having a model. So again, we're taking this intentional stance. We've got this physical system. It's engaging with the world. It's taking sensor inputs. Its state is changing over time. But we want to treat it as if it has a Bayesian prior. And the way in which we can do that is we can kind of define this map, this mathematical function that maps from the state space of the system to the world of probability distributions. because a Bayesian probability distribution doesn't exist in the world. But the physical state of something can parameterize a Bayesian probability distribution. So you kind of impose this interpretation on the system. And the idea is that when the system changes over time because it interacts with another system, then because we've got this function mapping states to beliefs, the belief is also going to change over time. And what we would like is for this belief, when the belief changes over time, we would like it to update according to Bayes' rule. And that kind of corresponds to sort of, in some very vague sense, saying that this square has to commute. But we can make that not vague and very formal, and you can read the papers on that. I'm not going to explain them, but I will come to a similar conclusion about mapping the states of the system to its beliefs. That's something we're going to arrive at later on, a different version of it. So that work was just on understanding, like, what does it mean for something to have a model, and what does it mean for something to act according to that model? But there's a bunch of results here and there dotted around in the literature in various different fields. There's a bunch of results that say something along the lines of, if an object of type X is optimal in some sense, then it automatically has something that we might call a model. So an example that might be quite familiar is the complete class theorem, which says, in the context of statistical decision making, that if you're an optimal decision rule in some sense, then you're automatically also a Bayes optimal decision rule, which is one that can be derived by assuming it has a prior and then makes decisions by expected reward maximization. So there's also this thing called the good regulator theorem that I'll talk about shortly, for most of the talk actually. There's an idea called the internal model principle in control theory, which is closely related. And the work I'm doing with Simon McGregor is also a version of this type of claim, that if something is optimal for in some sense, it automatically has a kind of Bayesian type of model. So what I'm ideally really trying to do in the end is to unify these things in a common framework. I think here's like a fundamental underlying reason why all of these things are true. Like there should be one theorem in the end that all of these are just special cases of. Again, I'm not going to get close to that today, but that's the purpose of this in the end, is to really understand the relationship between optimality or satisfactoriness and having a model. So, okay, there's this famous paper called the good regulator theorem, and like I hated this paper for ages. To be perfectly honest, it's got some really cool ideas, but it's a super flawed paper. And one of the annoying things is that the title is called "Every good regulator of a system must be a model of that system." And so you would think they would have a theorem in the paper that says every good regulator of a system must be a model of that system, but they actually don't. So it took me a long time to grow to like this paper, which I now do. So you have to sort of regard it as a work in progress. They had some cool ideas, they didn't quite manage to make it concrete. But what they were trying to do is actually really interesting. And so what I want to do today is figure out if I can improve on it, if I can take what they were trying to do, turn it into something that I would think was cool. So their idea, there's more than one idea in that paper. So their idea is that you have these two systems. So one of them is called the system, and the other one is called the regulator. And so the regulator is trying to regulate the system, and the idea is that the regulator. So there are these disturbances which change the state of the regulator in the system. And the idea is that the regulator gets to look at the disturbance that's kind of disturbing the system, and then based on what the disturbance is, it gets to choose an action. And the idea is that there's a set of desirable states for the system, actually both for the system and the regulator. There's a set of good states, and the idea is it's a good regulator if it manages to keep the system inside the good states. That's roughly the idea. And I think what they're ultimately trying to show is that the one way you could design a regulator would be to say, well, I'm going to look at the disturbance D, then I'm going to figure out what the state of the system is, and then I'm going to choose my action based on the state of that system. And their idea is that's in some sense the only way you can build a regulator. That if you were to try and build a regulator some other way, it would like have a model anyway, like even though you didn't intend it to. So I think that's kind of a neat idea, but it does assume that the regulator doesn't get to observe the system, but it gets to fully observe the disturbances. So there isn't much hidden information in this, and so the notion of model is a bit not that interesting, but we can fix that. So when you first hear about this theorem, and this is sort of what I thought for a long time as well, you think, hang on a second, can that possibly really be true? Because aren't there lots of counterexamples to this? So a really famous example is this thing called a Brackenberg vehicle, which is a really simple design for a robot. I guess it's like a conceptual robot, but you could build one if you wanted. The idea is it has these two light sensors, and it has these two wheels, and each light sensor is just directly connected to one of the motors that drives the wheels. And so the idea is that if this one gets more light, then this wheel will turn faster, and so this robot will drive towards the light, right? So it kind of has this sort of goal-seeking behavior. It drives towards the light, but it doesn't really seem to have any internal state, at least nothing that persists over time. And so how could that possibly have a model of anything? But it's still able to do some sort of regulation. Another example is open loop control. So if you want to balance a pendulum in the upright position, one way to do that is to measure its position and apply forces to keep it balanced. But another way to do it is to not measure its position, not measure anything, but just vibrate the pivot point up and down at the right frequency. And apparently, if you do that, the pole will naturally stay balanced. So you can have these controllers that don't measure anything; they just take actions, and they're still able to regulate things. And so that seems like, well, how could that possibly have a model? And so there's lots of other examples in biology and robotics where an appropriately designed body means less work for a controller. And so if we want to have any kind of result that says optimality implies having a model, then we'd better be able to account for these. So I sort of said Conant and Ashby's definition of model is maybe not that interesting. So what do I want from models? Well, and we'll come back to all of these points. So I think a model should involve beliefs. The system should have beliefs about a partially observed system, and those beliefs ought to be updated when new information gets available. At least I think, like, not every notional model has to have that, but the ones that do have that are going to be much more interesting than the ones that don't, in my opinion. And the other thing is that if something has a model and it also has a goal, it ought to take actions that are consistent with that goal and with the beliefs it has. And then the third thing I kind of think a notion of model ought to have is that models can be wrong, beliefs can be wrong. So we want to say this system believes that the goal is over there, and that's why it's going over there, but the goal is actually over there, right? The system has false beliefs. The beliefs shouldn't have to be true. Okay, so that's the kind of introductory bit of what I'm trying to do. At this point, I want to give you kind of a fair warning, which is that I decided that given this very generous 2-hour time window, I was going to try and give a talk where I could kind of go into real detail about one of the points. And that might have been overambitious. So that might be a bunch of technical information in the slides that I'll skip over. But I really hope that everything will conceptually make sense. So even if I skip over some of the technical details, I really hope that it will make sense as a story. And so if anything is confusing, or if you want more detail, including the technical information, then please don't be afraid to raise your hand or unmute yourself and interrupt if that's possible. So, right. What we want to do is to talk about a system. The first thing we want to do is so we want to have a system that's coupled to an environment and they can interact. And one of them is going to end up modeling the other one or being a controller of the other one. So later on, we're going to want to talk about the same system coupling to different environments. And then we're also going to want to talk about couplings of more than one system. Oh, so sorry, terminology. I could have called this the agent. I could have called it the system or the regulator. I could have called this one the environment. But I decided to use the term controller and the term plant, just because the letters C and P, like A is actions and also agent, it gets annoying. So they're called controller and plant, but that's just arbitrary. So later on, we're going to talk about the same system coupling to different environments. We're also going to talk about coupling of more than one system, because if you have this kind of situation where you've got like say a brain that's inside a body, and then the body lives inside some environment, like, should I think of the brain as the agent and the brain is regulating the body and the environment? Like, or should I think of the brain and the body as the agent and the brain and the body are regulating the environment? Or should I think of the brain and the body and all the books on the bookshelf as the agent, and that's modeling all the other stuff? Like, so we'll talk a little bit about that later. And it talks mostly about how you would formally do that rather than about examples of it, just to also as fair warning. So I'll mostly only talk about the very minimal setting where it makes sense to talk about things coupling to each other. And so I'll talk about just discrete time, discrete state spaces, and everything is deterministic. I'm very confident that this generalizes to all sorts of other situations where you have continuous time, you have stochastic dynamics. But this simplest case is already kind of interesting, and so I'm going to focus on, and also I know the most about the simplest case, so I'm going to focus on that. The asterisk here is that having a really good generation to the stochastic case seems surprisingly hard. So Alex just turned his camera on. Does that mean you want to say something? No. Okay. Okay. Simplest possible case. So when we couple two systems, so each of these systems are open, they have inputs and outputs, but when we couple them together, they're going to make a closed system that doesn't have any inputs and outputs. So we're going to start by talking about what a closed system is. Closed system is also called a dynamical system. Normally, when we think about dynamical systems, we think of differential equations, but we're working in discrete time, in discrete space, so it's a lot simpler. So a dynamical system or a closed system is just going to be a set together with a function from that set to itself. And you probably have thought about this at some point in your life before. One way you can think about this is kind of like a graph. So we have this set of states, and there are these points in the set, these various different states the system can have. And this function h takes the state and just tells you what the next state is going to be, right? So as we well, what's happened to my, okay, as we watch time unfolding, the system's going to start in one state, transition to the next, transition to the next, transition to the next, and then in this case, it's going to keep on going around these 5 states forever. But, yeah. And then this is like the discrete analog of a vector field. So if you really had a continuous time dynamical system with differential equations, this graph really is like this vector field. So instead of things moving from state to state discretely, things move continuously along paths that follow the vector field. So very often I'm going to want to talk about subsets of the state space. And this picture is kind of helpful for that. So a subset of the state space is just a subset of the states. Sometimes I'll call those predicates, maybe. I might not use that word much, but that's how I think of them. A particular property that such a subset might have is called being forward invariant. So a subset of the state space is called forward invariant if whenever the system enters that set, it can't leave again. So this subset here is forward invariant because although the system can enter through this transition, once it goes into here, the system's just going around this cycle and it will never leave again. So that's a forward invariant set, but this set isn't because the system is able to leave the set. So that's going to be an important property, forward invariant. But I will also often talk about subsets that are not forward invariant. And in the vector field case, this becomes something like a basin of attraction. So the trajectory of the system can cross over this boundary in this direction, but it isn't able to come back out again just because the vector field always points inwards. Okay, so I'll occasionally use string diagrams in this talk. I plan to use these a lot more. This is some notation from category theory. So like there's category theory in the background of almost everything I'm saying, but I'm not really going to use it explicitly, and maybe until the very end. This notation comes from category theory, but I'm just using it as a convenient shorthand. So instead of writing h colon x to x like this, I'm going to write H as a box, and it takes an input and it gives an output. So you think of the input coming in from the left, gets transformed by the function, goes out along the right. We'll see more complicated diagrams later. And these are formal diagrams. Each diagram has a definite mathematical meaning. It's not just an illustration of an equation. It actually is an equation, but I'm going to use them pretty informally in the talk. Okay, so back to coupled systems then. I talked about what you get when you couple two systems because that seemed like a helpful thing to have in mind. But now I'm going to talk about what a system actually is that we're going to couple. So we're going to talk about what's called Moore machines. We're going to talk about Moore machines, which are a concept from computer science, but we're using them to model dynamical systems. So the things we want a system to have. So in this case, with the controller, we want whatever the controller is going to give actions that are in some set A, and it's going to receive observations that are in some set O. So we'd like it to have a state space. We'd like it to give outputs in A. We'd like it to take inputs in O for observations. And we'd like it to have some kind of update rule. So a really good reference for Moore machines and their many, many generalizations, including continuous time and stochastic dynamics and so on, is this book by David Jas Myers. It's called Categorical Systems Theory and is currently in the form of a draft on GitHub, but it's relatively complete and it's very good. So if you really want to get into, especially when it comes to later on the stuff about composing systems, that's a really good reference. But here we're just doing the basics. So a Moore machine consists of a set called its state space, a function called the readout map, and this function is going to take an element of the state space, and it's going to give us an element of the set of actions, right? So it'll take the state of the system and tell us which action it takes on this time step. And then there's also going to be an update map U. And what that does is it goes from O times S to S. So what that does, it takes in the current state, it takes in the observation that the system receives, and it tells us the next state. And the way to think about a Moore machine is that it first gives an output and then receives an input, right? Whereas there are other machines called Mealy machines which take their input first and then give their output, but today we're not really going to talk about them. They are kind of important though. So a Moore machine first gives an output and then receives an input. And in these diagrams, which again, they are formal, but we're thinking of them in a pretty informal way. The idea is you start with the state, you send that state into the readout function and it gives an action. That action gets sent to somewhere else. And then later on, an observation appears from somewhere else and it gets fed into the update map, and then you've got the new state. This is quite a helpful way to think about how Moore machines operate. Does that that should become clearer later? Okay, that seems to be fine. So it should become clearer later if it isn't clear now. So in this situation, I've got a controller, it couples to a plant. We've got two Moore machines. One of them has an interface AO. The other one has the opposite interface OA, right? Because the plant has to give observations as output and has to take actions as input. And so we can couple them like this. This is ad hoc. Later on, we'll talk about a much more systematic way to couple systems together. Here, we're just going to draw this picture. So the idea is that they both give their outputs first. So the controller is going to choose an action. And at the same time, the plant is going to choose an observation to give to the controller as a function of its state. And then after that, this one will receive, the plant will receive the action from the controller, and the controller will receive the observation from the plant. And again, this is a formal diagram, and this crossing of wires means a definite thing. But like informally, just the signals travel along the wires, and that's all you need to really think about. So so in more traditional notation, that means this thing, which I find much harder to read. So the new state, the old state P, C, P is the state of the plant, C is the state of the controller, maps to this new state of the plant and this new state of the controller, where this is given by the updating the old state of the plant with the output from the controller, And this one's given by updating the old state of the controller with the output from the plant. So we'll call this H, and it's a closed system. Its state space is SP times SC. Make sense? So it's a closed system, and its state space is the Cartesian product of the two state spaces of the two systems that got coupled. And so we might think of it as looking something like this, right? So if P has 5 states and C has 3 states, then the Cartesian product is going to have 15 states. And then there'll be some dynamics on that, which are a consequence of these readout maps and update maps. And if we were in continuous time and continuous state spaces, then we might think of it, and I often will draw it as a vector field on, like if SC and SP were both one-dimensional, it'd be a 2-dimensional vector field like this. And the dynamics are a consequence of the readout maps and the update maps. So hopefully that's reasonably clear. Interrupt if it isn't. Let's go back to think about good regulators. So I'm going to say lots and lots of obvious things. And if I do my job, I'll only say obvious things, but I kind of think it will probably get difficult at some point. I don't know. So anyway, back to Conant and Ashby. Their definition of good regulator involves this thing called a good set. So in our case, I'm just going to define the good set is a subset of, so remember this was the state space of the joint of the combined system. So there's going to be a subset of that we're going to call good. And we'll say the controller is a good regulator if it's possible for the combined system to stay in the good states indefinitely. So that means if we start the controller and the plant in the right initial state, then they will always stay in the good sets. And then shortly I'll unpack what that means formally, like how to say that formally. But I just want to sort of talk informally about what that means. So if we were doing control theory, then we might have, then we probably would have that the plant is the thing we're trying to control, right? So I use this term controller and plant really suggests the plant is the thing you're trying to control. We don't really care about the state of the controller, except that it's used to control the plant. So it might be that the controller is supposed to keep this airplane within its acceptable attitude range. And then if we were to look at this kind of vector field where this direction is the controller state and this direction is the aircraft's attitude, then this set of good states is going to be this rectangle like that, right? Because as long as doesn't matter what the flight controller state is, the state is good as long as the aircraft's attitude is within its range. But in biology, it's kind of the other way around. So in biology, normally the controller is an organism, or at least one application in biology is that the controller is an organism. And in that case, the good set is a subset of the controller states, because an organism usually wants to stay alive, right? So if this is supposed to be a lizard basking in the sun, because that helps it keep its body temperature in the correct range, right? So now in this case, the good set is like it doesn't really matter what state the environment's in, as long as the temperature is in the right range. So there's lots of precedent for thinking about things this way around as well. Okay, so I said it has to be possible for the joint system to stay in the good states. So let's unpack a bit what that means. So that has to mean that there exist trajectories of the system that start in the good set and stay in the good set forever. But we don't require all trajectories that start in the good set to stay in the good set. So maybe if the airplane is stalled, maybe we can't keep its attitude straight, or maybe that would be a bad idea to keep its attitude straight. I'm not sure that's a great example, but. So what does that mean? It means that there must exist a non-empty subset of the good states that is forward invariant. So the idea is, as long as you start, so here we've got, this is the good set. We want to have a subset of the good set that is forward invariant, meaning that trajectories, if they're in the blue region called R, will never leave the blue region, and therefore will never leave the green region. So it's okay for trajectories to leave the green region, but they're not allowed to leave the blue one. So we call this, so if this exists, then we call it a regulation relation, or at least that's my name for it. I think in control theory, it might be sometimes called the controlled invariant subspace, and I think it probably also has other names. But I call it the regulation relation, and the reason I call that is because it's a subset of SP times SC, so that's a relation between SP and SC. So it's a subset of SP times SC that has the properties of being non-empty, because if it was empty, that would just mean that there aren't any paths that stay in it. So it has to be non-empty, it has to be forward invariant, meaning that paths don't leave it, and it has to be good, meaning it has to be contained in G. And so if we can exhibit such a set, we say the controller is a good regulator. So that means that to talk about good regulators at all, you need these four different things. You need the system that is the controller, the system that is the plant, the subset G, which you've decided are the good sets, the good states, and also a subset R of G, which is forward invariant and is non-empty, and that's called the regulation relation. So you need all four of those things if you want to talk about a good regulator. And we'll come back to that point. So here is going to be the thing. Here's going to be the thing that I call a model. I mean, yeah, like I said, just a reminder, I'm going to say lots and lots of obvious things, and if I do my job, everything will be obvious, but let's see. So if I have a relation between SP and SC, or any two sets really, so if I have a relation between any two sets, I can form a function, I can convert that into a function so I have a relation between B and A, I can convert that into a function from A to the power set of B. And that function is given by, so it takes an element of A and it just maps it to all the elements, the set of elements of B, right? The subset of B that's defined by all those elements of B where A comma B is in the relation. I will want to pause here and see if that was unclear to anyone, because if that isn't clear, then the rest won't make any sense. So the relations between A and B are in one-to-one correspondence with functions from A to the power set of B. Looks, yeah. So, yeah, in other words, another way to think about it is that the B is in I guess I called it row. If B is in row of A, then if B is in row in A, if and only if A comma B is in R. And so a way to think about this in this two-dimensional view. So if we've got some set R like this, we've got some value A and A, then I'm going to look at all of these values of B that are in R, right? So in some sense, we're going to have row of A2 is equal to these two line segments, right, which is a subset of B. And row of A3 is the empty set. Okay. So in our case, in this case of these two couples Moore machines, this is a map from the states of the controller to subsets of the states of the plant. And I'm going to call this map psi, because I don't know, it sounds like it stands for something to do with minds, I guess, psi. And I'm going to argue, I'm going to claim that this is a thing that it makes sense to think of this as a model. And that claim only makes sense to the extent that I can convince you that this thing behaves like a model. It behaves kind of like Bayesian updating. So we're going to think of psi. So for a given state C of the controller, we're going to think of psi of C as the set of states that the controller believes the plant might be in. Right. So that if P is in psi of C, the controller thinks the plant might be in state P. If it's not in state if P is not in psi of C, then the controller thinks there's no way the state is in that the plant is in that state. there's kind of like a probability distribution, but where all the probabilities are kind of 0 or 1 over n, right? We care about possible or impossible, but not about more likely or less likely. And later I might say a bit about why that is, because it's kind of forced on us. So coming back to this picture, psi is this map that I talked about, having this map that kind of takes the syntax of the physical state to the semantics of its beliefs, right? So this is psi is this map. The thing psi is mapping to is subsets of the plant states. Yeah, I already said this beliefs are possibilistic rather than probabilistic. And then, yeah, the reminder, beliefs here are attributed by an observer. I talked about that from the beginning. We're thinking about what it means to treat something as if it were an agent rather than what it means for it to actually be an agent. And what that means here is that G, the set G and the set R are kind of constrained by physics in some way, especially R is kind of constrained by physics. You can't, like, not every set is forward invariant, but you still have a lot of choice about what to think of as the good states and what to think of as the regulation relation. So this isn't, we're not looking at properties of a system, we're looking at properties of a system and also a set of good states and also a regulation relation. So yeah, so this only makes sense to call psi a model if it behaves like a model. And so I have to spend a bunch of time, yes, it probably like it's actually going quicker than I thought, but I have to spend a bunch of time convincing you that psi indeed does behave like a model. So there are three things I think are important for a model. I told you earlier, but I'm going to talk about two of them now. One of them is that the thing doing the modeling should update its belief consistent with information it receives. And the other thing that is that if the model is trying to achieve a goal, which it is in this case, it's trying to keep things inside the good states. If it's trying to achieve a goal, it ought to take actions that make sense that are kind of consistent with its goal and what we think of as its beliefs. And updating the beliefs doesn't have to be Bayesian, but it will usually be similar to it. And in this case, we'll kind of sort of see that it is similar to it. Like I think it sort of basically is Bayesian, but without all the probabilities. So I'll address number one first. The modeler should update its beliefs consistently, and then two later on. So for thinking about belief updating, we can kind of ignore the good set G and only think about the set R. Now remember that R is a forward invariant subset. That's going to be the important thing that makes belief updating happen. And we're going to remember that we're looking at a combined system that is formed by coupling these two Moore machines in this way. So, right, this is the update function that determines the new states, and it's given by this. And more slowly it's just that we update the plant based on the action taken by the controller. We update the controller based on the observation generated by the plant. So since R is forward closed, we have that that if P and C are in R, then P prime and C prime must be in R. If P prime and P prime and C prime are given by H, P, C. So, or equivalently this, right? Because P and C being in R is just the same as P being in psi of C. That's the definition of psi of C. So equivalently, if P is in psi of C, so if the state P, if the controller when it's in state C believes that the plant might be in state P, then the controller when it's in state C prime, which is the updated state, has to believe that the plant might be in state P prime, which is the updated plant state, right? So that sounds kind of reasonable. If the controller believes the plant might be in state P at one time step, then it has to believe that it might be in the successor state at the next time step. And these belief updates depend on the observation that the controller receives, because Because this is psi of C prime, right? The posterior beliefs, if I can call them that, are given by psi of C prime, and C prime depends on the observation, and the observation depends on the state of the plant, right? So these beliefs are changing as a function of the observation. So there's a nice hint that there might be some kind of sensible notion of updating happening. Similarly, the state of the plant is going to update based on the action that the controller takes, right? So the thing that the controller is reasoning about depends on the action it takes. And so the idea here, and this is the thing that I hope is going to make sense. And I'm going to say this and then pause afterwards and see if it makes sense or is obvious or is not obvious or what. This thing I hope is going to make sense. So what we should imagine the controller doing, because remember, the controller is just a thing, it's just acting, it's just physics, there's nothing mysterious going on, but we are attributing beliefs to it. We're treating it as if it were an agent. And the way in which we should be treating it as an agent is that we should sort of imagine it's thinking like this. So it thinks, well, I previously believed that the plant was in one of the states of P, which is psi of C, right? The prior beliefs. Previously believed it might be in one of these states. But then I received this observation, O. And so I can narrow that down because only some of the states in P would have emitted that observation O. So I can take my beliefs and I can reduce them down to a subset because I got a new observation. And then having done that, I also know that I took action A. So later we'll talk about action selection, but here we just say it knows it took action A, knows which action it took. So I always took action A. So I knew it must have been in one of these states in Q, one of the ones that would have emitted O as an observation. But I also know I took action A. So that means the plant's now going to be in a new state. It will be in one of the states given by this. It will be in one of the states that are a successor state of one of the states in Q given action A, right? So now I have this new set of states that I think that the plant might be in. And so this is the kind of possibilistic version of Bayesian filtering, if that makes sense. So P is the prior over the plant state at the previous time step. Q is the posterior over the plant state at the previous time step. And then P prime is like a kind of posterior marginal of the states of the plant at the current time step rather than the previous one, given by kind of simulating the updating of the plant. So if you were a controller, you might want to reason like that because that's a very logically correct way to reason. Unfortunately, our controller doesn't actually do exactly this, but there's a good reason. So if the controller would use exactly this Bayesian type of reasoning, then we would have to have the psi of C, which is the posterior marginal beliefs about the new state of the plant, would have to be equal to this, which is just the above written out in longer form. You don't have to read the equation. But in fact, we only have that the new states are a superset of this. And so the interpretation is that the controller is allowed to forget information that it no longer needs. So if you forget information, then you enlarge your set of possibilities, right? Because you're forgetting constraints. You're saying, I know this thing is over there, but actually I don't need to remember that it's exactly there. I'm just going to remember that it's in that general area, right? So the set of possible places it can be always gets bigger when you forget information. So the idea is the controller does do this kind of discrete Bayesian filtering, but it also forgets information if it doesn't need it anymore. And this is the point where I'm going to pause because there's a sort of a you can try to prove that it's actually kind of tricky and fiddly and annoying, but I want to see if this makes sense or if it just seems weird. Go ahead.
I just have a question. I'm not sure if I've understood it correctly, but because we're talking about this thing being forward invariant, does that mean there's some upper bound to how big psi of C can be? Or like will it always can it can it start to believe that it's in possibly in some states that are like definitely not possible for it to be in. And if it does this, happen in an unbounded way.
Yeah, I mean, it can happen because because of this forgetting step. So this forgetting step can actually arbitrarily increase the size of the beliefs. So it's definitely possible. I mean, actually, like another way to think about it is
right.
Like we could always choose, because we could choose G and R, right? So we could make G and R as big as we wanted, and then then we would just say, well, the goal is to do anything at all, it doesn't matter. And then the beliefs are just, well, I believe it's in some state and I don't care, right? Because my goal is to do anything. So I don't really care about keeping track of the state of the plant. So like I guess that's sort of a flavor of this interpretation stuff that I do with Simon and Martin, that we always permit these trivial things, right? The interesting thing is that it's possible to attribute sensible beliefs to a system, but we don't care about preventing you from attributing silly beliefs because I don't know, like we just don't. Did that make sense?
Yeah, it made sense. I think I was trying to think of an example where the belief is sensible and it still assigns, like in the math, there might still technically be states that it might think it's in that are like somehow non-physical. And if that's a problem.
Yeah, where it is a problem or where it isn't.
Where like that happens, but it's not a problem.
Yeah, so I'm sure there are like I ought to be able to come up with such an example. Let me think for a second. Like I don't know, it's not a great example, but like if you can, like you play this game and you look to see whether the switch is in this state or this state, and then if it's in this state, like you have to press this button, and if it's in this state, you have to press this button. And the game is you're gonna go into this room and you're gonna do that, and then you're gonna go away, and then you're gonna come back and you're gonna do that again, and you're gonna go away. And actually the state of the switch never changes, right? It's always in this state, and you always have to press this button. But like if you forget, it doesn't really matter, right? Because like so it's in this state, you press this button, fine, you go away. Now you think it might be in this state because you just forgot. But that doesn't matter because when you come back, you'll just see it's in this state and you can press the button again.
Yeah, that makes a lot. Yeah, this is a good intuition pump. Thank you. I think I'm following up.
Okay. Good. So this reasoning is a possibilistic Bayesian version of Bayesian filtering, and if we permit the controller to forget information, it can never assume information it didn't have, right? So we're not like it's like it can forget what it knew already, but it can't just magically know things that if it doesn't get information. This notion of updating just follows from this R being a forward invariant subset. So this notion of regulation that we came up with implies this notion of belief updating. Fine. So the controller can forget, which I already explained. So this covers the way of updating beliefs in a Bayesian. The point one about models, they have to update in a Bayesian way. Now we cover point two, which is the selection of actions that are consistent with the goal, which is regulation in this case. So the goal is keeping the system in the good states. So the controller's task here then is to keep the plant controller system in the good states. I think I'm going to skip some technical details and might come back to them, but the basic idea here again is that that we have to think about so we're thinking about action selection. So before we just said, oh, it takes this action A and it knows what the action was, but now we're thinking about like imagining it deciding which action to take. And the reasoning that we want to attribute to it looks like this. It says, I know that the plant is in one of the states in P, like psi of C, my prior beliefs, and I know that those are all good states. Why? Because R is a subset of G, right? So R is a subset of G. So the controller had better always think that the plant is in a good state already, because its goal is to keep it in the good states. And if it might not already be in a good state, then it would have failed already. So even if it thinks it might be in a state that isn't good, it better assume it's not in that state, because if it isn't, then I mean, if it is in that state, it's over already. There's nothing you can do, right? So you might as well just assume it's definitely in a good state. Okay, so it knows that those are all good states given its current state, and then it has to choose an action. And the idea is, it says to itself, I don't know which state the plant is in. It's in one of the ones in P. I know that, but I don't know which one. So I had better choose an action such that whatever state it's in now, the next state will be in G. The next combined state will be in G, right? Because if you're like no, and if I can't choose such an action, I'm already dead. I'm not a good regulator. So I better choose one such that the new combined state will be in G. But actually, that isn't even enough, because it might be that the new state is in G, but then from that state, there's nothing I can do, right? It could be that the next state is in G, but after that, it will leave G no matter what I do. And that would be bad. I'd better avoid that too. So I'd better kind of do it recursively. I'd better make sure that the next state is not only one that's a good state, but it's also one that I know how to regulate it, right? So I better make sure that when it goes into the next state, I will know how to keep it in the ones I know how to regulate recursively. And that turns out to be basically, so firstly, that's a version of Bellman's principle. I don't know if Bellman's principle is familiar. Bellman's principle is a classic result from kind of POMDPs and that type of, or MDPs and that type of maths. And it basically says, if a controller of some kind is optimal at a state at time t, that means it's optimal at time t plus 1 as well after it's updated its state. That idea is called Bellman's principle, and this is kind of a version of it. But the point is that this holds automatically because R is forward closed, right? So R being forward closed means that the next state will still be in R. So in fact, we can, like, I mean, I'm hand waving a lot here because time's running relatively short, but we can attribute this kind of reasoning to the controller. So it does take actions in a way that really makes sense in terms of an intentional story that you can tell. So that's it. That's the thing. That's the simple and obvious thing I wanted to spend ages telling you. Sorry. If we accept this argument, then we've proved something that could in fact be phrased as every good regulator of a system must have a model of that system. If we accept that that's a sensible notion of model, it's just true. Like every good regulator does have to have a model. But this is much more, well, as I said here, it's much more interesting. It's more general than Conant and Ashby's one, because our systems are partially observed, our models have belief updating, things are dynamic, and it's all cool. So what about those counterexamples that I mentioned? Well, the idea is that although models exist, they can be more or less trivial. So this theorem isn't a magic bullet. It actually doesn't do what Conant and Ashby would have wanted, because it says yes, everything has to have a model, but that model might just be I don't care. So a Bratenberg vehicle has trivial internal state, so psi of c can never change, but it still exists, right? So if you're lucky enough as a controller that you never have to remember anything, then you can just be optimistic. You can say, well, I believe the world is in a good state, and I'll just do the things I always do, and the world will stay in a good state, and that's great. And I never have to worry about anything. So you still have a model, it just doesn't update very interestingly. And the same kind of story can be told about these open loop controller. It never gets any information to update its state, so it never really changes its model. But it doesn't mean it doesn't happen. Yeah, in the embodied robot controller case, the robot controller does get some information, but it can be a bit lazy. It can say, I don't really care where my feet are because my legs have the right frequency to just make walking happen anyway. I don't have to worry about it. So this is going to be a bit of a vague idea, but I think it's a good idea. I don't really know how to do it properly. But the idea is that the big difference between sophisticated agents like human beings or, sophisticated AI systems or whatever, the big difference between those and simple things like Roombas is that they differ enormously in kind of how much the model depends on the controller state. So if you look inside a Roomba, you don't really learn very much about the room it's in, right? It just has very simple sensors. It's a very simple memory. You can't learn very much from looking inside it. But if you would look inside my brain, you could tell what my parents look like and all sorts of other things about the world. And the reason for that, I think, is basically that when you look at the shape of this G and R for a really non-trivial agent, they're going to be these complicated, crazy fractal things, right? So that then when you look inside the controller state and you find psi of C, you'll like it will really depend in a very weird and non-trivial way on C. So that's kind of all I'm going to say about that. But I think that's like a really good direction for figuring out like why the intentional stance is useful. So I want to talk about other notions of regulation. So because I've been like, I kind of started out by saying what I really want to do is like capture this general idea. And I've talked about one specific case, and I'm going to talk a bit about how to generalize it. So I defined regulation as being about keeping the system inside the set of good states. But if you're into control theory or whatever, you might prefer something else. You might say, well, actually, no, I want the system to try and put the system into a good state. Like I want it to be like a goal that the system, like it hasn't been achieved yet, but the system wants to achieve it in the future. And you can totally do that, right? Or you can say, I want the system to put it in a good state and then keep it in the good state. And if it goes out, I want it to put it back. And we have a nice framework. I'm not going to give the details right now just because of time and it being another very long technical thing. But we have a nice framework for this kind of thing based on modal logic, where you can really kind of plug in your notion of regulation and ask for, and then kind of get some similar thing to all of this out. And it ends up being very, very similar. The reasoning you attribute to the agent is very similar. More broadly than that, you can also change the notion of Moore machine. So we kind of talked about discrete state and deterministic updates. Both of those things can be relaxed. I have a very good idea of how it works in the continuous time case. The stochastic case is weirdly difficult. I think I mentioned that earlier. But we have some work on it. And the notion of good set is this binary thing. You're either in the good set or not. But of course, you might want to talk about a value function, for example, which is more of a continuous thing. And that's also possible. I haven't done everything I would like to do with that yet. I have a suspicion that there'll be some kind of complete class theorem type thing when you work with value functions. That means your prior won't be binary, but it will be genuinely probabilistic. But like that, I haven't figured that out yet. It just doesn't seem particularly easy, because basically the reason these priors are possibilistic is kind of because G is absolute, right? You're either in R or you're not in R, so therefore your beliefs are zeros or ones, and it'd be nice if they would turn into probabilities, but I haven't done that yet. I mentioned about models being wrong, but then all the way through I talked about the true state of the plant, and I never really mentioned models being wrong. But that's actually kind of easy to fix if it's just like a simple logical step. So the idea is simply that if you only gave me the controller and you didn't give me the environment that it lives in, you only gave me the controller, I could still define the model as the plant and the subset G and the subset R of G. And that plant, this model plant, doesn't have to be the same as the real plant. Does that make sense? It's not very complicated. It's just like I can just define models such that I allow them to be wrong using the same framework. And again, like this is useful because you want to be able to talk about studying something in an environment other than its natural environment, and then so okay, that's a simple point. Want to close by talking about more than two systems because this is where all the really interesting stuff is in. But I'm going to whiz through it super quick because it takes a whole lot of mathematical formalism to really talk about. So previously we did this ad hoc coupling where we took these two systems and we just crossed over the wires and said that's the coupled system that you go. Let's take that apart and build it back in a better way so that we can figure out how to do it properly. So first we took these two systems. That's what we started with, right? The plant and the controller. They had these opposite interfaces, and we thought of them as this sort of diagram with a hole in it. So we can take these and we can compose them in parallel. So we're not going to cross the wires. We're just going to kind of stack one on top of the other. This is again a Moore machine. So the readout function is now this, which is actually the function that maps P comma C is going to get mapped to O comma A, simple as that. Right, so that's a function that takes in something in the Cartesian product of SP and SC and gives out something in the Cartesian product of O and A. And then the update function is something that takes in the Cartesian product of A and O and also the Cartesian product of SP and SC and gives out something in the Cartesian product of SP and SC. So it's again, it's a Moore machine again. And so we can kind of draw it, well, I'm waving my hands a lot now. This is all stuff you can read about in the David Chasmai's book that I mentioned. I'm really going to wave my hands a lot and say we can introduce a whole new type of diagram that looks similar to the old ones, but they're different. And we're just going to draw this system like this by kind of putting these diagrams in putting these two systems in parallel with each other. And you should think of it as kind of like this. Before we had the plant and the controller talking to each other, now we just have them with their outputs and their inputs going to some other place. But then once we formed this system, which still has a hole in it because it's a Moore machine, we can just put that little cross wires thing in the box, right? And so when we do that, we get a closed system again. So what am I doing? I'm just moving things around and saying the same thing in a different way, but that's what category theory is all about. The point is that we're going to think of this as, so we're still thinking about coupling these two systems, but the way in which we're coupling them is we put them in parallel and then we compose them with this weird thing that connects the wires, right? First we put the systems in parallel, then we compose them with another thing that connects the wires together. So fine, we put these two things in parallel. We put the crossed wires thing in the box. Fine. We can put something else in the box if we want. I'm waving my hands even more now because I'm really not going to explain this, although I can if people want me to have more time. We can put some other stuff in the box, and that's called a lens. And the point of a lens is that it lets you compose things in a more flexible way than just connecting wires together. So we have a way of taking two open systems with kind of dangling wires that want to connect to something else, and we can compose them in a way that lets them connect to a third system if we want to, right? And well, I guess I'm not really properly explaining how you compose them like that, but the answer is it's arbitrary. You get to choose, and I'll give more detail if you want me to later. This lets us compose open systems to get open systems. I already said that. There's a whole theory of this, but I won't explain it, and it's in this book. I already said that. What this allows us to do, the point of this, is that it lets us talk about multiple connected systems, like the brain and the body and the environment. Or if you know Clark and Chalmers' famous paper on the extended mind hypothesis, you could talk about Otto and his notebook and the environment. Otto's a forgetful person who can't remember where he lives unless he writes it down. So it says, Otto, is Otto the agent, or is Otto and the notebook the agent? So the formal framework that I've described but haven't explained lets us split the same system up in different ways in a very formal way. So let's just say we have these three coupled systems, and I'm literally going to put two of them together and call that the controller, and one of them on its own and call that the plant. Or I could put the brain into the controller box and the body in the environment box. So this is just to say that you can do everything super formally. You can talk about this more than two things coupling. And the point here is that we started with this kind of like partition of the world into agent and environment, right? Like I just started with that, like this system is the agent, this one's the environment. Then we proceed from there. But what we can do instead is start with the whole system, the joint system, and just ask about ways to factor it into an agent and an environment, right? There may be many, many such ways that we could do that. And this formalism allows you to think about all of the ways in which, well, in principle, allows you to think about all of the ways. I haven't done things like counting them, but you could. So there may be many ways to factor something into an agent and an environment. But the good set and the set R that we talked about, these things were just subsets of the joint state space. So that doesn't really change when you partition the system differently, right? So you're saying like for example, this organism is trying to stay alive. You can keep that fixed. I believe this organism is trying to stay alive. While you vary the boundary, like I consider the brain to be the agent and everything else to be the environment, or I consider the body and the notebook to be the agent and everything else to be the environment. So you can change the boundary while keeping the goal fixed if you want to. And if you do that, the belief map is going to change, right? It's going to look different. So I guess all I want to say about that, but unfortunately don't have a good example to give you. I really wish I did. I didn't have time. That probably, in some sense, depending on where you put the boundary, the model agent story is going to make more or less sense, right? Like if I say the boundary, the goal is to keep me alive, but the agent is that cup of water, it's not gonna do much, right? But if I say the goal is to keep me alive and the agent is me, then that's gonna do a lot more. So in future work, I really hope to be able to quantify like interestingness or usefulness of the agent perspective. But let's move on to the conclusions because this is basically the end. So I've showed in a simple setting that every good regulator of a system has to have a model of that system in a certain sense, where the model involves a kind of possibilistic Bayesian updating, and that arises very, very naturally, just from like basic definitions in control theory. Look at it the right way, where you take this relation and turn it into a function, and then you got this thing that behaves like Bayes. So it's kind of really suggestive, at least, that there is this very general notion that notions of optimality produce notions of models automatically. So I think the following things are general principles. They're given a notion of optimality or of kind of good enoughness, there will be a corresponding notion of model. And they're given an appropriate version of Bellman's principle, there will be a corresponding notion of belief updating that will typically resemble Bayes. And I think these principles can be formulated mathematically in the language of category theory, and that's ongoing work. Yeah, optimality is always going to be subjective, because in addition to physics, you have to choose the goal, you have to choose the regulation relation. You're never going to be able to get those unambiguously from physics, in my opinion. But some choices are generally going to make much more sense than others. And then there's a whole other load of open questions of like, why are there agents at all? And, how does evolution produce agency and all that kind of thing, which I'm also really interested in and working on, but aren't part of the talk. And that's it. So hopefully we can have some discussion.
Yeah, amazing. I mean, thank you so much. First of all, this is really, really, really good and really informative. Yeah, I'm gonna leave it to, I have a bunch of questions myself, but I want to let the audience go first, if there are any. So if there's anyone, feel free to jump in. There's also a Q&A function if you don't want to type yourself. But given that there's quite a few of us, I feel like I'm just gonna let anyone jump in if they want to.
Could you just state the sort of theorem version of your good regulator theorem?
Yeah, that's a good question, isn't it? So I guess if I wanted to state it as the theorem, I would first have had to, I should have done it in a different order where I first define what a model is, and then I say, aha, theorem, this model automatically exists. So the theorem is going to be something like, if So it's going to be something like define a model, this particular type of model, as a function from the states of the controller to subsets of the plant, and let us say this model updates consistently if it obeys this thing up here with a subset sign in it, wherever it's gone. It updates consistently if it obeys this equation. And we'll say that actions are chosen consistently if they obey some other condition that I described in words but didn't put an equation for, I think. So we define a model as that, and then the theorem is that every good regulator has a model.
Cool, okay. I also had some questions about, you said in the beginning, like you're presenting the simplest, most discrete version of this thing. I had some questions about, extensions.
Sure.
You did mention generalizing the good set to a value function. I assume you meant like a utility function, like elements get mapped to the real line, and yeah.
Beg your pardon, yes. The good set would become a utility function or a reward function, and like conjecturally, the regulation relation R would become a value function.
Yeah, one way that I often think about optimizing or good regulating or whatever, improving this environment somehow, is according to just an order relation over the states and not necessarily a value function. I was curious if that seemed easier or harder to extend it to.
Let me think for a second. So, so the usual thing in let me gather my thoughts. So you need some way to talk about, like, you need some way to state Bellman's principle one way or another. And that means that you need some way to relate performance at the current time step to performance at the next time step. And there's various different things you could choose there. So the typical thing in like POMDPs and so on is that you add the reward at the time steps with possibly with an exponential weighting. Right, that's one thing you could do. In the work with Simon McGregor, we don't do that. We say instead that you want to maximize the probability of some goal being reached, and that corresponds to multiplying the rewards at each time step, because probabilities don't add, they multiply in this context. Right, so that's another option you have, is to multiply the rewards at each time step. Another option might be to take the minimum or the maximum or something like that. The reason I'm saying this is that if you only had a partial order, then like adding and multiplying wouldn't make sense. But you could still do things like maximizing or minimizing. So these things are sort of like anything's possible in a sense, as long as you have all the bits you need. Yeah. And then there's also, like I could mention von Neumann and Morgenstern's theorem here as well, right? Which kind of says if you have a partial order on a probability simplex that's compatible with things in the right way, then it's just the same thing as having a value function anyway.
Yeah. And the Bellman principle thing that you're referring to, is that idea that like an optimal thing will, or I guess it was like, if you take the optimal next action, then that means that you'll take the optimal next action, right? So is a generalization maybe that like, if you increase expected utility on the next step, then you're expected to increase expected utility on the next step? Something like that?
Oh, wait a second. Yeah, I guess so. Yeah, so I guess the way I think about Bellman's principle, which might not be the way it's normally stated, I'm not really sure.
Mhm.
The way I think about Bellman's principle is roughly along the lines of, suppose I have an optimal policy that I'm going to follow, and then I take the first step of that policy I receive. So my policy might be like a game tree type of thing. I'm going to take this action, and then as a function of my next sense of value, I might take this action or this action, and then as a function of the next one, I'll take this one and this one. So the idea is that if I take the first action in that policy and I receive my next sense of value, then the rest of my remaining policy, the rest of the tree descending from that node had better be optimal if I would just start from that node. Right, because if it wasn't, then that would be pretty weird, right? I'd take an optimal action and my policy would be optimal, then I'd start doing my policy and it suddenly wouldn't be optimal anymore. But then if that's the case, why didn't I just do the thing that would have been optimal to start with, if you see what I mean?
Yeah.
Yeah.
I have a question about, I guess also maybe an extension, or maybe it's something that already appears in the current thing, which is something like with Bayesian updating, there's this thing of like, in the general case, it's uncomputable. And so there's a sense in which I kind of expect the agent to be doing some kind of like approximate updating. Does your subset notion already capture that, or is there some extra machinery you need to include to like track something like yeah, like in like
I'm embarrassed to say I
bounded
don't
rationality.
know the answer. I've been thinking about that for a couple of years and I don't know the answer. Yeah, so yeah, approximate Bayesian updating is really weird and I don't quite know how to think about it. So it might be related to the thing about that's around here somewhere. It might be related to the thing about the agent being allowed to forget. Because that sort of seems like an approximation-ish thing. But I've never really got that to work formally. In the sense that I've never really seen how you could start with this framework and then get some. Sorry, I'm just trying to sort my screen sharing out. It seemed to freeze. Yeah, I've never really seen how you could start with this framework and then get something like variational Bayes out of it, which is a bit disappointing. I always wanted to be able to do that, and I just don't really know how.
So my guess is something like, I wouldn't expect optimality to imply bounded rationality. I'd expect like something like bounded optimality to imply bounded rationality. So my guess is something like you'd need to have some notion of the good set being fuzzy, or some way of being like, we allow, yeah, like we don't need this thing to be perfect, but we can talk about like sub-perfect things.
Yeah, I kind of share that intuition. Yeah, so I mean, like that part of it's easy enough to do, but it might not be the right way to do it. But you can just say, well, instead of requiring, so I still have all the utility function and the exponential weighted discounting or whatever, right? I still have all that machinery, but instead of requiring it to be optimal, I just require it to be good enough, like above a threshold. Right, your goal is to earn at least this much reward, and beyond that, it doesn't matter. Then I kind of expected that would lead to a notion of approximate Bayesian updating, and perhaps it does, but I don't really know, and there might be a better way to do it.
Yeah, once again, my instinct there is that's a little bit like crass or something, that like I want to see is something like a trade-off between like exploration, exploitation. I want to see something like, yeah, your optimality being like somehow coupled to how good your model is or something.
Yeah.
Also, like maybe a different frame or something, which is going to be a different question of mine, is near the end you just said this thing of like, oh, you might do this question of choosing a goal, a good set, and then asking what boundaries are sensible agents. To me, like maybe I instinctively kind of thought the opposite question, which is like choose a boundary and then ask what is its goal? Sort of for this.
Mhm.
And there I wouldn't be surprised if like you can make that question into one where it's like you can imagine there being like more or less precise goals, where it's better achieving the less precise goals and worse achieving. And then if there's some kind of trade-off between how precise the goal is and how good it is at achieving it, this might get to the like notion of boundedness.
So on that point, like just entering my head as you say it, I've not really thought too much. For some reason, I've not thought too much about that question before. I'm not sure why, because it sounds like an obvious question. But let me try and find a good diagram that I can copy and paste. I have one somewhere. Let's take this one. All right. So for this one, I chose. Let's just copy it out here. So for this one, I chose like this relatively large G and this relatively large R. Well, let's get rid of G. So R has to be forward invariant, right? And then G doesn't really have any constraints. Once I've chosen R, there's no great constraint on G other than it has to be a superset of R, right? So for this agent, like I chose this forward invariant set, but I could have chosen a smaller one, like this one. I think that would have been a perfectly good one. And I could have even chosen a smaller one, like that is basically just exactly equal to this to this attractor, right? So limit cycle. So I could have, that's the smallest, like in some sense, or it's a minimal regulation relation that I could have chosen. So that's in some sense like for this system, because all the other trajectories seem to go off somewhere else. Maybe for this system, that's the only reasonable or the most precise reasonable goal you could possibly choose, right? Because I could then just make G equal to that set, and that would be like a really minimal goal I could have this system follow. And then, well, I don't know. Yeah, you talked about trade-offs between how good it is and how precise it is and stuff like that. Like, yeah, there's all sorts of, because you could, like, yeah, it's another of these trivializing things, right? You can always just say the goal of a system is to do exactly what it does.
Yeah.
But then that's not a very, like, if my goal is to just say exactly these words, that's not a very satisfying way to think of me as an agent. It's really, my goal is to explain something and not to say these exact words.
Right.
I had a similar thought about approximate Bayesian reasoning. The version of this problem that I think about is if you have these two separate entities that are connected with the input output, and you see that the environment or plant side is like, you see that those states tend to go up some ordering, where I think of it as like you can implement the thing across many different dynamics, and like across the dynamics for any given dynamic, it tends to go up the ordering. Then what can you say about the internals of the controller? And I try to think about it as like, it doesn't go perfectly up it doesn't go up the ordering as fast as possible. It doesn't like definitely get inside any particular subset, but like if somehow on average in the weakest possible sense, it does better than random at going up the ordering, then it seems like that should imply some degree of modeling what dynamics it's currently in. But it would be like a very, very weak version.
Yeah, I mean, I would, like, if I understood right, yeah. So you're sort of saying in a stochastic context, you've got like some measure of goodness in it, and the goal is for that to increase, basically. Then I would imagine that the same phenomenon would happen. That one day I would like to be a theorem, but I'm just, it's an informal thing. But I would imagine the same thing would happen from the conclusions, that there will be a corresponding notion of model of some kind, and I don't have an immediate intuition what it would be.
Another slightly wider question is, have you had any thoughts on the notions of interacting agents and maybe something like cooperation or communication. Like I want to be able to say something like good cooperation requires communication or something, which feels like it's like interactive version of the same principle.
Yeah, so I've got lots of thoughts about that live in totally different formal settings than this one. I've never, I mean, like this like only occurred to me like a couple of days ago. Like, oh, I should try thinking about multi-agent systems in this framework, and I haven't really tried it before. But yeah, there's lots of other stuff that I think about, like about that kind of would be pretty interesting to explore in this framework. The like a lot of goal-seeking behavior is actually a coordination problem. Like me at one time can be seen as a separate agent from me at a later time, and those two have to agree on a communication strategy, right? I have to encode my thoughts in a way that later me can decode correctly. And that's in some sense why it's really hard to train recurrent neural networks, because you have this like coordination problem between the encoding and the decoding all the way across time. And that must somehow relate to this idea of this, like there being a semantic interpretation of the states that I've been talking about, but I don't really know currently how that concretely relates, but it's a really interesting thing to think about.
Amazing. All right, we're an hour and a half into the total thing. If there's more questions, we can keep going. We have another half-hour time box.
I have a meta question. Do you have a paper or post or anything that has some or all of this content in it yet?
No. So yeah, this is the first time I've kind of tried to explain it to anyone other than my collaborators.
Cool.
So yeah, there will be sooner or later. I mean, there's a draft in progress, but there's papers on like on the model side of it from more of a Bayesian probabilistic perspective, like basically this picture. This is long. Like there's the papers that make this picture completely formal, but they don't really talk about the theorem side of it, where you say like if it's a good regulator, then it has a model. That's forthcoming.
I see.
Nice. Yeah, I remember talking to Martin about this at the A-Life conference, and we had a similar set of discussions around approximate Bayesian updating and the relation to active inference and these kind of things. But yeah, we can get into this another time, I guess. Yeah, do you have any more comments, or does anyone have another question?
Yeah, I can pose one.
Oh, lovely.
So since the regulator is part of a closed system and it has beliefs, wouldn't it have to have beliefs about its own beliefs? And then recursively have beliefs about those. Is this handled, or is this outside of this model?
I've never thought about that in this context before. Give me a moment to see if anything comes to mind that I can say about it. I think there's not much I can concretely say about it, other than to say that in this framework, we attribute beliefs to the system, and I've talked about attributing beliefs to the controller about the states of the plant. But there might be ways to attribute beliefs to the controller about other things, such as its own beliefs. It's a pretty interesting thing to think about, but I don't think I have anything concrete to say right now.
Well, thank you.
Yeah, I'd also be really interested in that in the multi-agent setting with like agents that have beliefs about each other's beliefs.
Yeah, I'd love to do that. Yeah, like, I mean, I've only thought vaguely about this, but like you could. So this is definitely answering your question. So but vaguely. So I'd love to know what it means for an agent to attribute beliefs to another agent, right? So here, like, we have this magical observer who does the attributing, but you could have an agent attribute beliefs to another one, which would mean that I, as an observer, attribute beliefs to this agent about the beliefs of this agent. And that would make sense in an interacting thing. And then, of course, once you've done that, you should be able to have an agent, like you as an observer should be able to attribute beliefs to an agent about itself as an agent, right? Because we reason about ourselves as agents, right? Or, you know, I'd better make sure I do this before I do that, because otherwise I won't want to do that, and I'll get distracted or whatever, right? We reason about ourselves as agents, and so if you had this whole framework for doing that, you could do that kind of thing.
Mm-hmm. Cool. Any more? I'm also enjoying this kind of free will thought thing that we've ended up in. So if people want to continue spitballing, I'll give like 30 seconds for people to come up with something.
When you mentioned that the stochastic version is difficult, my first question is which parts are you making stochastic, and then what's difficult about it?
So it's difficult because, so it's easy enough to make a theory for interacting stochastic systems. That's in David Jasmeiser's book already. The belief part of it is just a bit more difficult, really, because, well, so it would be easy. So if you would keep the same notion of goal that I have here, right, where the goal is to stay inside the good states with absolute certainty, then nothing much would change. Actually, it would be basically the same as it is here, because the agent's beliefs would still be possibilistic, because it doesn't care about anything other than whether it's possible to stay inside the good sets or not possible, right? That's a binary thing. But once you start having value functions in there, and also the probabilistic things, and you would really like it to work out that or at least I would like it to work out that the agent is doing like genuine Bayesian reasoning. It just gets difficult, because you're putting these things in and you're hoping to get this thing out, and you won't get the thing out that you want unless you put things in just the right way, and it kind of gets difficult for that reason. Also, because when I was trying to do it before, I was maybe over ambitious, and I was trying to do everything with like standard Borel spaces and measure theory. I probably should have just stuck to finite state spaces and discrete probability. But
another thing that's coming to mind is I don't know. I know other people I've talked to who are asking similar questions have often come across this problem. The best word I have for it is like ontological crisis, which is a situation where an agent has to come up with a refined version of its world model. So the concepts it had before don't apply in the future. So it's something like, like it's almost like shifting which world you believe you're in or something.
And specifically, there's a thing where if your values are, or if your goals are encoded using a certain ontology, and then you have a belief update so that those don't even make sense anymore, then there's a crisis of like, how do I even make sense of my values?
Yeah.
Yeah, I mean, I guess, I mean, I agree that's a problem. I guess this framework is kind of almost designed to make it go away because, you know, like everything's a nicely defined set, right? But I mean, you can obviously have things like what would happen. Like you actually, a version of that happens in this framework as I explained it, because I kind of papered over this super quickly. But when I talked about having wrong beliefs, so if the agent's beliefs are wrong, so the agent believes that the plant is in the set P of states, and then it receives an observation from the plant, and then it says, well, I'm going to narrow that down to only those states of the plant that could have emitted that observation. But if the model is wrong, that could just be the empty set, right? That it could receive an observation that, according to its model, is simply impossible. And then if that happens, then it's sort of undefined what happens next in a way. Well, it just means its beliefs are the empty set, which means that it thinks like that's like believing false, right? So, but that's kind of analogous to what happens in probability if you get a data that's outside the support of your prior. But that's, I guess, it's not quite this notion of like needing to completely expand the space that your beliefs are in.
So my intuition here is to build like a two-step process where you have a set of models over different worlds, and you kind of do interpret as an agent in each of those models. And then you can imagine the probabilistic thing as being a prior over what world the agent thinks it's in. But then it's deterministic within each world.
Okay, that kind of makes sense, yeah. So I have a probability distribution over worlds, and then each one's deterministic. I mean, yeah, you could, but why did you suggest that? What does the...
So one thing is something like, if one of your worlds you receive an empty set, then the probability of being in that world goes.
I see. Yeah,
And
okay. So you could sort of design a way to, yeah.
I guess it also links to, I don't know, Scott Garabrandt has this idea of like generalized probability, where you have like a probability distribution over probability distributions, with the main idea being you can like formalize the difference between being 50% sure something's going to happen and just not having a model of it at all. And one nice thing about this as well is that, like, yeah, from the view of like this behaviorist view of trying to understand what an agent is doing, you can see the inner probability as like a value that it assigns to different worlds, and it's just a different interpretation of the same thing, where instead now it's a probability of different worlds, and each world, it doesn't have probabilistic beliefs, but it has like different values that it puts on things. And then understanding it as like an expected utility maximizer, just saying it maximizes the expected value times probability. And there it's like, it's this notion of value times probability that is the actual key notion, rather than each of those individually. I think I butchered some of it there, but my guess is that like this kind of thing could pop up in this formalism as well.
Yeah, I mean, that all sounds like stuff you could do within this framework, yeah. Yeah.
Cool. Last chance for any brainstorming, popcorn comments from people before we wrap up.
Cool. Well, thanks so much for the discussion, everyone. That's actually been quite, like, it's been really good to sort of explain this and get some thoughts, and it seemed like it wasn't boring. So, so that's a data point. So it's helpful. Thanks.
Yeah, this talk was very, very related to my interests, so I was quite happy to hear it. Thank you.
All right. Yeah, amazing. And also like glad that we got to have this like brainstorming session at the end. It's a big advantage of a small group. So
yeah,
that's nice. All right. Thank you everyone for coming. Thank you, Nathaniel, again. We'll be in touch about the possibility of uploading a recording, or maybe part of this. But yeah.
okay.
Thank you for talking.
All right.
Bye.
Thanks, everyone. Bye-bye.